Hey everyone, welcome to section 1.2 types of data. We are continue working with the introduction to statistics. Let's begin by talking about what's the major concept of this section. And the major use of statistics is able to collect and use sample to make conclusions about populations. Again, we are using a sample to make inferences about a population. Remember, a sample is a subselection, whereas a population is every member. Let's talk about a definition, parameter. A parameter is a numerical measure describing some characteristic of a population. So parameter goes with population. You're describing a measurement of a population specifically. Whereas a statistic is also a numerical measure, but now this time you're describing some characteristic of a sample. So make sure you note the difference. So a parameter goes with population, a statistic goes with a sample. So statistics and samples go together. Parameter and population go together. We also have types of data. We have quantitative data. Quantitative data or numerical data as well consists of numbers representing counts or measurements. So we can have some examples such as weights of supermodels, the ages, heights, different types of numerical data that I'm given. Those are some examples of quantitative data. We also have categorical data. Categorical data is more of a qualitative attribute. For example, it doesn't consist of like an order, or it doesn't represent any counts or measurements. Categorical is more of names, labels. An example would be a gender, male or female, right? Or numbers on a shirt. So they're not by ranking, it's just you can have some numbers that are represented in a back of a jersey or so. Those are examples of categorical data. Now, how do we work with quantitative data? Well, quantitative data can be further described by distinguishing between two things, discrete and continuous types. So this is for a quantitative data. Because a quantitative data represents a quantity and a numerical. So it could be splitted by a discrete or continuous type. So we'll talk about what that means. A discrete data is results when the data values of a quantitative are finite or countable. So it reaches up to a number of times. So the number of tosses before getting tails. So let's say I have a coin, I toss it, I'm going to get a head, but eventually I'm going to get a tails. So it's an experiment that terminates. Okay. So you're going to do, there's going to be data that eventually it's going to terminate. Whereas a continuous data of a numerical can result of infinitely possible quantitative values where the collection of values is not countable. You're going to say, well, the length between 0 to 12, that's countable. But wait a second. So if we have 0 to 12 centimeters, within each centimeter, there's little tiny meters like 0.001, 0.0001, so on and so forth, which it can be infinitely many times. Okay. So that can result in infinitely many possible quantitative values. Levels of measurement. Another way to classify data is by the 4 levels of measurement. So we have the nominal level, which is the most basic level, and then it gradually moves up: nominal, then ordinal, then interval, and then ratio. So there's 4 levels of measurement for classifying data. Remember, we have the quantitative and we have the categorical data. The nominal level is mostly names, labels, and categories. So for example, yes, no, and undecided would be a nominal level. Yes, no, or undecided is not quantitative. So the nominal level is more of a categorical data. The nominal level. Ordinal level involves data this is key. It can be arranged in some order between data, but it could be meaningless. So we know that course grades, we know that A comes before B, before C, before D, before F. This ordinal level has order. It's in the name. So an ordinal level has order. It can be arranged in some order. Interval. Now this one's a little bit different because an interval level of data involves data that can be arranged in order, and it has differences that can be found meaningful. However, there's no natural zero. So for example, when you're trying to arrange years, right? There is no natural zero. It doesn't belong from 0 to so on. So 1 BC, 2 BC, but it does not contain a natural zero. There is no natural zero. That is key. Now the ratio level, that's the difference. The ratio level, it's data that can be arranged in order. The results are meaningful and there's a natural zero. Now, the class time between class times of 50 minutes and 100 minutes. So we begin from 50 to 100, where your starting time is at 50 minutes. So you know from 50 and 100 minutes, class times of 50 and class of 100. So from 0 to 50, from 0 to 50 minutes, or from 0 to 100 minutes. But we know we have a starting point. So for example, if our class starts at 10:10 and ends at 11:25, we know our starting time is our natural zero, where it starts. It has a starting point. That is the key of a ratio level. It has a starting point. Now let's look at the summary of levels of measurements that we just saw. The nominal are categories only. Ordinal categories with some order. Interval differences, but not a natural zero. Ratio differences and a natural zero. So the most intense level of a measurement is the ratio because it contains differences and a natural zero point. So it has a zero, it has a starting point, and there's differences. More the nominal and the ordinal are categorical type of data. Interval and ratio could be considered, of course, quantitative data. Okay. Now let's look at big data. What is big data? What does that mean? Well, big data refers to sets so large and so complex that their analysis beyond the capacity of a traditional software tools. So in order for you to perform big data requires significant software. So for example, the government collects big data of a population or a particular state. It will require significant software to be performing operations running in a parallel on many different computers. That involves data science. It involves applications of statistics under computer science and software engineering, along with other relative fields such as sociology and finance. So when you're working in the sociology field or the finance field, even the medical field, involves data science as you're running statistics of huge things that require software engineering and computer science to be running those programs and being able to identify that big data and being able to kind of give you the results of what you're looking for. There's also something called missing data. So we looked at quantitative data, categorical data, types, levels of measurements. We saw a big data, data science, and now missing data. Well, In statistics, there's also room for error where we had misleading conclusions. It's a data value is completely at random if a likelihood of being missing is independent of its value and other values in the data set. That is that any data value is just likely to be missing as another data value. So for example, you're inputting data, you're a software engineer, and let's say you miss one little detail that kind of ruins everything. You have missing data that's completely at random or purposely missing. A data value is missing, not at random, if the value is related to the reason that it's missing. So sometimes data analyst kind of reserve some data, that way it doesn't interfere with a conclusion that they want. So you can have a missing data completely at random, and then there's one that's not at random. So those are the two types of missing data. Either be completely at random or not at random at all. How do we correct this for missing data? We can delete the cases. So one very common method for dealing with missing data is actually to delete any missing values or input missing values. So we input missing data when we substitute values for them. So there's two ways of correcting. So you either delete the case or you input missing values. So you actually substitute. So you substitute or delete. Those are the two different ways of correcting, missing data. And with that, we finish our section of 1.2. And let's us continue to section 1.3. On 1.3, we are collecting sample data. What types of data are we collecting? What type of sample data? So the key method used to collect sample data influences the quality of the statistical analysis. So it is very important to know what method is being used to collect sample, because that will make a difference on the quality of the statistics analysis. One particular importance is a simple random sample. If a sample are not collected in an appropriate way, then the data must be so orderly that no amount of statistical torturing can salvage them. So it's very important the way that you collect your data, making sure that is accurate and you have validity. The gold standard is randomization with the placebo treatment groups is sometimes called the gold standard because it's so effective. So hopefully we all know what that means. So a placebo, such as a sugar pill, has no medicinal effect. So you don't know as a patient whether you're actually given the actual pill or a placebo, which is a false sugar pill, that can kind of influence on your behavior. If you're being told by a medical person, hey, this is a Tylenol, this will make you feel better in the next few hours, and you're actually just getting a sugar pill. So how that kind of influences that. The basics of collecting data. Statistical methods are driven by data that we collect. We typically obtain data from two distinct things. We do it from observational studies and experiments. These are the two typical sources that we use to obtain data. We either observe a study or we actually do the experiment. The experiment is that we apply some treatment and then proceed to observe its effect on the individuals. So for example, the individuals in the experiments are called experimental units, and they are often called subjects when they are people. So subjects are referred as people that are being treated with this experiment. Whereas an observational study, when you have an observational study, we are just basically observing and measuring specific characteristic without attempting to modify the individual's study. So you're not actually doing anything to them, you're just observing and measuring, that's it. So there is no modification, no treatment here in the observational study. So that's what you want to have down. Let's look at some examples. Let's look at an example with ice cream and drowning. Observational study. We observe the past data to conclude that ice cream causes drowning. This is based on the data showing that the increase on ice cream sales are associated with the increase in drownings. The mistake is to miss the lurking variable of temperature and the failure to see that as temperature increases, ice cream sales increases and drowning increase because more people swim. So if we have an observational study, if we're just looking at two things, we're seeing the increase in ice cream sales versus the increase in drowning, we can't really make an assumption that ice cream and drowning, that ice cream causes drowning, right? Whereas an experiment, when we conduct an experiment with one group treated with ice cream and the other one has no ice cream, we see that the rate of drowning is about the same in both groups. So ice cream consumption has no effect on drowning. Here, the experiment is clearly better than the observational study. So that means that when we're doing a type of test, such as an observational study, in different cases, we can get a false negative. Whereas in this case, for an ice cream and drowning, the experiment was obviously a more adequate choice because we were able to treat one person that gets an ice cream while the other one doesn't, and the rate of drowning is about the same. So the ice cream consumption has no effect on drowning. So we get clearly two different possibilities. So here the experiment is clearly better than the observational. And that actually depends on what type of study you're doing or conclusion you're doing. How do we design experiments? Well, one of the things is by replication. Replication is the repetition of an experiment done on more than one individual. Good use of replication requires sample sizes that are large enough so we can see effects of treatments. So what does that mean for us? That means that the larger enough sample we have, we can see the effects on the treatment. So we do need a large enough sample so we can see the effect on the treatment. There's also blinding effect. The blinding effect of an experiment right now is the blinding effect, which is the placebo effect, is that the subject does not know whether he or she is receiving the actual treatment or a placebo. A blinding way is also around the placebo effect, which occurs when an untreated subject reports improves in symptoms. So again, this is your brain telling you, oh, I did actually get better, when in reality, this person was actually untreated. There's also exists the double blind, which is the blinding occurs at two levels where the subject or the person, remember the person, or the patient, that's the subject, doesn't know whether he or she is receiving the placebo, but also the experimenter. So also the person conducting the study. Does not know whether he or she is actually administering the treatment or placebo. So that creates a more effective technique because it's called the double blind. And of course, there exists the use of randomization when you're creating your design of an experiment. Randomization is used when subjects are assigned to different groups through the process of random selection. The logic is to use always chance way to create two groups that are similar. So the logic is to use chance. So randomization occurs at a random basis. Okay, it's more of a logic to use chance. Now, the definition of a simple random sample. A simple random sample is a sample of n subjects, we don't know how many, is selected such a way that every possible sample size n has the same chance of being chosen. A simple random sample is often called a random sample, but strictly speaking of a random sample has a weaker requirement than the members of a population that have the same chance of being selected. So a sample size or a simple random sample is more selective in a way, or more strict. So a simple random sample is a strict way of randomization versus just a random sample. So there's a difference. So one is stronger than the other. The simple random sample is stronger. It has a more stricter way versus just versus a random sample in general. Now, this section 1.3 involves, so remember section 1.3, what we're doing right now involves sampling methods. That's what we're looking at, sampling methods. Well, we're going to talk about the types of sampling. The first one we see is called the systematic sampling. That means after every case. So let's say that I'm in my class and I'm purposely selecting every third student. So 1, 2, 3, you're in one group. 1, 2, 3, you're in another group. So every third. 1, 2, 3, you're selected. 1, 2, 3, you're selected. 1, 2, 3, you're selected. That is called a systematic way of sampling. There's also the convenience sample, where this is the data that's very easy to get through a survey, through just walking around campus, trying to get people's input, convenience sampling, something that it's very easy to get, data that it's very easy to get. There's a stratified sampling, where you actually have to subdivide, this is key, you have to subdivide the population in at least 2 different groups. So let's say you have, I have a room, I want to split 2 groups, women and male, and then from each group, I select another group. So then I draw a sample from each subgroup. So first I cut my population, I subdivide it in 2 groups, for example, or even ages, if you're age blank to blank, blank to blank, and then I do, okay, men and women. So I'm stratifying my sampling. So you do 2 subdivisions. You subdivide the population first in 2 subgroups, and then within those subjects, I do another subgroup with the same characteristic, and then I choose a sample from each subgroup. So I kind of subdivide. I divide my first population, and then I pick from each. There's also the clustering, where this was not subdividing, but you divide the population in area or clusters. Then some of those clusters, then we randomly select some of those clusters and choose all of the members from each cluster. So for example, I pick 3 different streets. I divide my area, so Chula Vista area, and then I have Bonita area, and then I have, the east of Chula Vista, the south of Chula Vista, the north of Chula Vista, and the east, and then I just grab some from all of them. And then I just grab from all. Then I have the multi-stage sampling, where it means that I'm collecting data by using some combination of basic sampling methods. So first I want to design posters, select data sample, and then I go into different stages. And then at a different stage, I might use a different type of sampling. So for example, I could begin with a subdivision, and then I can do a cluster, and it's a multi-stage. So it kind of builds on. So the multi-stage is something that builds on. So as I move in my study, I choose different methods. That is multi-stage sampling, because you're not just at one stage. You're not just doing one type of sampling. You're doing one sample. At my first stage, I'm doing a convenient sample. So this can be an example. I could start with a convenient sample because it's easy to get a convenient sample. And then I want to say, okay, well then after that, I want to do a stratified. That would be, so stage 1 would be my convenient sample, stage 2 would be my stratified sample, and then the third one would be a cluster. And this is my multi-stage. So I started with a convenience, then I want to kind of stratify, I want to subdivide, and then I want to subdivide in areas and then pick from everywhere. That's a multi-stage sample. So observational studies observe and measure, but do not modify. So the ones that we saw up top, more of an experimental things that you can do, the blind, the double blind, the simple random sample, where that's all experimental. Observational studies, all you can do is observe and measure. You do not modify. What are the types of observational studies? There's called a cross-sectional study. That means that the data is observed, measured, and collected at one point in time, not over a period of time. So that would be at once. And that's a cross-sectional study, right? It's at the point in time. I'm going to collect it just right now. I'm not going to collect it in 10 years. There's a retrospective study that are collected from the past period and then going back in time through examination of records, interviews, and so on. So maybe, for example, if I had my COVID shot some time ago, and then what happened after, looking at past examinations, past records, something that happened from the past. Retrospective is something from past time. There's a prospective, or the longitudinal, that it's data collected in the future from groups sharing common factors, or called cohorts. And those are more of, we want to know what's going to happen if we collect data from now and from the future, in the sense of, okay, well, we're going to, based on what we see, this is what we're going to be predicting for the future. Those are called cohorts. Those are the 3 types of observational study: the cross-sectional, retrospective, meaning the past, and the prospective, or what's going to happen in the long run. And then we have confounding occurs in an experiment where the experimenter is not able to distinguish between the effects of different factors. So this occurs in an experiment. That's when you, the person who's doing the experiment, you're not able to differentiate the effects of different factors. So you try to plan experiments so that confounding does not occur. So you want to be very explicit. You want to know what you're actually are going to be experimenting, what treatment you're going to give, so then you can prevent confounding. What are the controlling effects of variables? How do we control these effects? Well, we use completely randomized experimental design. We assign subjects, so assign people or patients to different treatment groups through the process of random selection. We use a randomized block design. This block design is a group of subjects that are similar, but blocks different ways that might affect the outcome of the experiment. So for example, we can be talking about a particular block of people that have diabetes, or people that have high blood pressure, but some have different ages or things of that nature. So they have similar, they're similar in some kind of way, but maybe the experiment or the treatment can have a different outcome on each person. The controlling effects, it's also, there's another one that's called using matched pairs of a design. When we compare 2 treatment groups by using subjects and matched pairs, that are somehow related or have similar characteristics. So this is more specifically comparing two treatment groups by using subjects in matched pairs. So in pairs, I'm going to be doing these effects. That is why it's called matched pairs, because you're pairing the subjects. You're using the pairs of the subjects. Now, there's also the rigorously controlled design where you carefully assign subjects to different treatment groups so that those given the treatment are similar in ways that are important to the experiment. This has the most contribution. The rigorously controlled is where you are carefully assigning subjects to different treatment groups where you're going to have similar ways that are important to the experiment. So this one will have more contribution to the study because you're carefully assigning the subjects. Now, sampling errors always occur. Let's say that even though you did a multi-stage sample, you did a carefully designed. So now, no matter how well you plan and execute the sample collection process, there is still likely to be some error in the results. Some of them are sampling error or randomly sample error. This occurs when the sample has been selected at a randomly method, but there's some discrepancy between a sample result and the true population result. So remember, even though we're using a sample as a sub-collection to kind of evaluate the big picture, at the end of the day, we truly don't know what will be the true population result because we're always basing ourselves from a sample. So this is from basing ourselves to a sample, not a population, can result in error. Right? Because we're only grabbing a sample, we're not looking at the population entirely. And lastly, we have non-sampling errors, which is a result. So when you do a non-sampling is actually a human error, including such factors of wrong data entries, computer errors, biased wording, false data, responding, foaming biased conclusions, or applying statistical methods that are not appropriate for those circumstances. So the first sampling error would be more of a sampling error or random sampling error, or the other one is a non-sampling error, where it's more of a purposely type of thing. It's a human error, something that you're actually inputting wrong, or you are biased and you're not getting appropriate statistical methods. And the non-random sample error, is a result of using sampling method that it's not random. So you're actually doing a convenient sample or a voluntary. So this one is not at random, not at random. And that influences getting a sampling error because you're not getting the results that you want. So at the end of the day, one of the errors is using a wrong sampling error, a random sampling error that can occur. It's still a simple random sample or as a sample, but there's a discrepancy, right? Because this always occurs. There's the non-sampling error, where it's more of a human error, a biased, or there's a non-random sample that you purposely selected a convenient sample or a voluntary sample that does influence your statistical study. So those are the three things that you have to look at when you're looking at sampling errors. And with that, we terminate chapter 1. So in this sections, we saw 1.2 and 1.3. Remember, 1.2 was looking at the types of data that we had. So make sure that we review. So we saw types of data in 1.2 and collecting sample data in section 1.3. And with that, we terminate chapter 1. So hopefully, as we are reviewing, you're also taking notes, because there is a chapter test and there is a lecture recording attached to this lecture on 1.1, 1.2, and 1.3. Good luck, and I will see you all for chapter 2. See you soon. Bye-bye.